A nuclear reactor does not make electricity directly. It first makes controlled heat. Read the chain from left to right. Atom split, hot core, steam, turbine, electricity. Once this map is clear, every later detail becomes easier to understand.
Fission starts the heat. The plant's machinery moves that heat in a controlled path. Everything else in the plant exists to control that chain safely and steadily.
Fission begins when a neutron is absorbed by a heavy nucleus such as uranium-235. The nucleus splits into fragments and releases energy, mostly as heat inside the fuel. It can also release more neutrons, which may trigger more splits nearby. In a reactor, the point is not a blast. The point is steady heat production. Control systems keep that chain reaction useful instead of letting it run away. The fuel is not loose powder. It is ceramic pellets sealed inside long metal tubes. Look at the exploded view: pellet, cladding, rod, and then a larger assembly. Many tubes are held in a precise grid so water can flow between them. That geometry spreads heat across a large surface area and keeps the core predictable. Fuel design is already part of control, cooling, and safety. Inside the reactor vessel, fuel rods sit in water. The water carries heat away, and in many designs it also slows neutrons down. Slower neutrons are more likely to keep the chain reaction going at a useful rate. The core is doing two jobs at once: moving heat and guiding neutron traffic. The vessel around it keeps pressure, flow, and geometry under control.
Control rods are the brake pedal of the reactor. They absorb neutrons instead of letting those neutrons continue the chain. When the rods lower into the core, more neutrons disappear from the chain. The reaction slows down, and the heat output drops in a controlled way. When rods rise, more neutrons continue, so power can increase carefully.
Heat must move away from the core continuously. In this simplified pressurized water-style diagram, hot primary water flows through a closed loop. The pump is the muscle of the loop. It keeps hot water moving through the path. Valves and sensors help control where the heat goes and how fast it moves. The loop carries heat while keeping the reactor side separated from the turbine side. The steam generator is a heat exchanger. Hot primary water passes through tubes, while water outside those tubes turns into steam. Heat crosses through metal, but the two water loops do not mix. That separation is why the primary loop can stay closed and controlled. Now the story moves from nuclear heat into ordinary steam machinery. Steam rushes into the turbine and pushes rows of blades. The spinning turbine shaft turns a generator, like a huge version of a bicycle dynamo. Inside the generator, motion through magnetic fields drives electric current. That current travels into transformers, and then out to the grid. The reactor made heat, but rotating machinery makes electricity.
After the turbine, the steam cannot simply be thrown away. A condenser cools it back into liquid water so the cycle can repeat. Cooling water removes heat from the exhaust steam through another separated loop. Cooling towers release mostly ordinary water vapor from that separate cooling loop. The important motion is cycle, not waste. Steam returns to water and goes around again.
Safety is not one magic wall, it is layers. Fuel form, metal cladding, reactor vessel, containment, sensors, and cooling each solve a different problem. The layers are strongest when they work together, not when one layer does everything. Operators and automatic systems watch power, temperature, pressure, and radiation. The engineering idea is simple: prevent, monitor, contain, and cool. Used fuel still produces heat after it leaves the core. At first, it stays underwater, which removes heat and provides shielding. Later, it can move into dry casks, thick containers built for long-term storage. The decay heat graph shows why time matters. Heat falls, but not instantly. Managing used fuel is part of the reactor story, not an afterthought. So the chain is: fission makes heat, heat makes steam, steam spins a turbine. The turbine spins a generator, and the generator sends electricity to the grid. Control rods, coolant, containment, monitoring, and storage keep the process stable. Every major object in the picture has a job in that one chain. A nuclear reactor is not magic. It is a carefully controlled heat engine.